Hello everyone. It is my privilege to stand before you today as Dr. K. Vijay from the Department of Civil Engineering. Our focus for this session is on the cornerstone of the modern structural engineering, the matrix method of structural analysis. This methodology has not only redefined how we approach complex structure, but also serves as a computational backbone of today's most advanced engineering software. Thank you for your presence and I look forward to engaging with you throughout this presentation. To ensure a comprehensive understanding, our discussions will be structured as follows. We will begin with the introduction to the matrix method, contextually its importance. This will be followed by the refresher on key matrix algebra concepts essential for grasping the technical foundations. We will then delve into a flexibility matrix method, exploring its principle and applications. Next, we will examine the stiffness matrix method, which is the most widely used approach in the contemporary practice. We will discuss the software computer implementation of this method, highlighting their roles in modern softwares. Finally, we will conclude with the summary and practical case studies to illustrate real world applications. The matrix method represents a systematic numerical approach for analyzing a statically indeterminate structure, unlikely a classical method which rely on manual iteration techniques. This method employs matrix algebra to establish precise relationship between forces and displacement. It may develop to address the limitation on traditional methods such as moment distribution and slope deflection method, which become practically for large scale structure. Today, the matrix method forms the algebraical foundation for industry standard softwares like SAP 2000, StatPro, ETABS. The core idea involving discretization of a structure into finite element, each represented by a matrix, assembling these into a global matrix systems and solving for unknown displacement and force computability. Need for matrix method. The advent of matrix method was driven by the inherent limitation of classical approaches. Classical method, while effective for determinate or low order indeterminate structure, prove inadequate for modern engineering challenges. For instance, analyzing a high-rise building or a long-span bridge using moment distribution would not be only time-consuming but also prone to errors. These methods lagging of generality and scalability required for today's complex structure, which often features irregular geometries, dynamic load, and sophisticated material behaviors. Uh, Matrix method addresses these challenges by offering an unified and systematic frameworks. They are capable of handling structure with any degree of indeterminacy, accommodating various load cases, boundary conditions, and material properties. Moreover, their formulation and inherently compatible with computer programming, making them ideal for the finite element method. The compatibility ensures accuracy, efficiency, and consistency in result, enabling engineering to tackle projects that we once deemed infeasible. In essence, matrix method serves as a critical linking between theoretical mechanics and computational innovations. To appreciate the paradigm shift, consider the contrast between classical and matrix method. Classical method rooted in manual calculation or between limited to small scale application. Matrix method by leveraging computational power excel in handling large complex systems. They eliminate the need for case specific techniques, providing a generalized approach that applies universally to beams, press, frame, and grids. This transition has only enhanced analytical capability but also revolutionized the design and safety assessment of infrastructures worldwide. A firm grasp of matrix algebra is essential for understanding this method. Key operation includes matrix addition and subtraction, which require matrix of identical dimensions. Matrix multiplication, a non-cumulative operation fundamentals to assembling system matrix. Matrix transposition. which involves interchanging rows into columns. The columns becomes rows and rows becomes columns. Matrix inversion, a critical step for solving system of linear equation. These operations collectively enables the representation of structural behavior in compact mathematical forms. The flexibility matrix method, also known as the force method, is one of the two primary approaches. Here, the unknowns are redundant force and displacement are expressed as a function of these forces using the flexibility matrix. While this method is conceptual, aligned with classical forces, effective for low order indeterminacy. It offers from limitation. The selection of redundant is not only straightforward and the process become increasingly cumbersome for highly indeterminate structures. Consequently, it is very largely superseded by the stiffness method in computational applications. Next is the stiffness matrix method. Um, the method or displacement method is a cornerstone of modern structural analysis. In this approach, the unknowns are the nodal displacement and the forces are related to the displacement via the stiffness matrix method. Its advantages are manifolds and it is inherently systematic, applicable to any structural type and capable of handling arbitrary levels or indeterminacy. Furthermore, it seamlessly integrates with computational algorithms, forming the basis of finite element method. While manual solutions are feasible, only for simple structure, software implementation effortlessly managing large scale system, delivering precise and reliable results. So the matrix method are the bedrocks of all major structural software platforms, and the programs such as SAP 2000, StatPro, ETAPS, utilizing these materials methods to represent individual systems, beams and column stresses as effective stiffness matrices. The advantages of matrix methods are profound and multifaceted. Generalized, they provide a unified frameworks for all structural types, from simple 2D frame to 3D model. They adapt effortlessly. Precision and computability efficiency, adaptability. These are the advantages of the matrix methods. And limitation, computational demand, input sensitive, linear assumptions, expertise requirement, and they are not suited for the hand calculations beyond simple cases. This is all as far as the limitations is concerned. The practical implementation of the matrix method is realized through softwares. SAP 2000, re-owned for its versatile in analyzing building bridges and individual structures with robust capability in dynamics and seismic analysis. StatPro, a preferred tool for designing and analysis across the diverse projects, supporting compliance and with international codes. ETAPS, specialized for high-rise structure, integrating advanced structural analysis with design automation. These tools exemplifies the translation and theoretical principle into engineering solutions. Um, in conclusion, the matrix method of structural analysis stands as a testament of engineering innovation, enabling the realization of the structure that pushes the boundaries of design and functional ability. It integrations into computational tools has empowered engineering to create safer, more efficient, and more resilient infrastructures. I thank you for your attention, and once again, thank you.